We'll start with our first speaker. That is Eric PERRIN, who is Associate Professor at the Research Center in Information, Communication Science and Technologies at the University in Reims. And you're going to talk about the implementation of AI algorithm for the detection of vine diseases. What we decided is that we have, I hope all speakers know, you have 20 minutes of talk, and then like this, it gives like 10 minutes of questions. So we're starting now, and we're going to finish at 11:15 French time, which makes 12:15 for UK. So Eric, the floor is yours now.
I will share my slide.
Yeah.
You see my slide?
Yeah.
Okay, thank you. So I will talk about the implementation of AI algorithms for the detection of vine disease. As Hélène said, my name is Eric PERRIN. I am an associate professor and the coordinator of the Inter-Teams Research in Smart Agriculture within the CReSTIC laboratory in University of France. There is the summary of my presentation. I will talk about the main challenge of disease detection in vineyards. Then I will explain the utilization of artificial intelligence for diseases detection in viticulture. I will talk about the development of robust AI algorithms on embedded system for the detection of vine disease. And I will finish with the presentation of the performance and the limitations of the current tools, and try to explore some research avenues to improve the detection. Detecting vineyard disease and addressing the global heating are critical challenges in agricultural and climate science. In vineyard, disease detection is essential for maintaining crop health and ensuring optimal yield. The global heating involves significant threats to agricultural productivity and ecosystem stability. The rising temperature can alter the growing condition and exacerbate water stress and increase the prevalence of pests and diseases. Moreover, extreme weather events associated with climate change, such as heat wave, can further impact vineyard health and productivity. To address this challenge, it requires interdisciplinary approach that combine scientific research, technological innovation, and policy interventions. The remote sensing technology combine multiple research methods, including satellite imagery and drones, can provide valuable insights into the vineyard health. And additionally, data-driven model can help to predict disease outbreaks. Today, in the Champagne vineyard, inspections are realized with traditional methods that often rely on manual inspection with human. These works are time-consuming. They may not detect disease at the early stage, and they provide sometimes very low detection level, under 30%, because it largely depends on the disease and its symptom expression that can be different from year to year. And they also may be different for the same disease between grapes varieties, by example, Pinot Noir and Chardonnay. The principal disease of the vineyard are the fungal diseases like oidium, mildew, botrytis, SK, black rot. There are also viral disease like leaf rot, And finally, bacterial and induced by phytoplasma diseases like yellow diseases, and especially the flavescence dorée, that is considered as the most dangerous one. The flavescence dorée detection is one of the main and urgent threats for the Champagne vineyard. A large part of the Champagne vineyard is made up Chardonnay. It's a white grape variety for which the symptoms are less visible than on red grapes varieties. And we must note that there is actually no cure for this disease, and detection means extracting a vine plant. All of these observations highlight the importance of developing new tools based on artificial intelligence. Artificial intelligence offers numerous benefits for disease detection, like the early detection, best accuracy and efficiency, meaning time saving, the scalability and sometimes predictive analysis. The inputs of the model are generally based on RGB or multispectral images and built on deep learning CNN, a convolutional neural network. The CNN is often represented by a big black box with in input the picture, as you can see here. And the picture are the vine leaf for our application. And in the output, the decision about the disease or the healthy leaves. The CNN must be trained with some 100,000 pictures of label leaves. So it's a big constraint. Despite multiple advantages, CNN have become increasingly cumbersome. They need more and more images to perfect correctly. And they also need an equal number of images for all classes for the training phase, which is impossible regarding the image of disease leaves, always in lesser number. It is particularly relevant for the flavescence dorée. Many CNN are not adapted for being implemented on embedded systems because of computational power and memory needs. And there is also another problem when we detect a new class, the CNN needs a training phase that can be time consuming. So we have decided to adopt a specific strategy. We want to have the control of the global chain that goes from the image acquisition to algorithm implementation and field testing. Because the implementation of effective algorithm alone is not enough. It is necessary to have the best possible data that are well suited for the disease we are seeking to characterize. Here is the synoptic of our strategy. In the beginning, we tried to find the best spectral band for the detection of a specific disease. Here we are working on the flavescence dorée, by example. Then we want to specify a well-suited camera and then conduct acquisition under controlled conditions and in vineyard plots. At the same time, we develop a lightweight and robust algorithm suitable for embedding on drones. And at the end, we test the algorithm after the harvest of the year n, n-1, n-2, etc. And we do the correction and the adaptation of the procedure and the algorithm for the next year n+1. The first step of our procedure is the acquisition of spectrum in a controlled condition, as we can see in this figure. The acquisition of spectra of vine leaves is made manually, and we collect about 2,000 spectra per year. We are developing algorithms to select the more sensible bands of the spectra for the detection of the flavescence dorée. Those algorithms use machine learning and information theory. Our goal is to find between 4 and 6 bands and to specify a well-adapted camera to this disease. The bands must be quasi-insensitive to external parameters, such as varying weather conditions from one year to another. We have realized also experiments in controlled conditions, as you can see in the picture here. For now, as long as we do not have the suitable camera, we are conducting acquisition with 3 commercial multispectral cameras in the visible, in the near infrared, and in the short-wave infrared bands. You can see in this picture the different bands of the multispectral camera in near infrared, the blue, the green, the red edge, and the near, with the wavelengths. And in the lower part in the slide here, the SWIR camera. As you can see, the SWIR camera has only one lens and is equipped with a filter wheel and the chosen wavelengths. It is very important for us because with the near infrared camera here, we can have some problem of parallax, but it is not the case with the shortwave infrared camera here. We realize acquisition in natural condition with one other camera, a parrot camera, in several plots of approximately 50 vine plants at a height of 2 meters, as you can see in the picture. Some acquisitions are also realized with a drone, DJI, at different heights, 10 meters and 5 meters, and with different angles to find the maximum numbers of leaves in one picture. As you can see here, here we have the best picture with a maximum of leaves in it. Our strategy of software development is to build accurate and lightweight CNN and fast operating model. We must keep in mind that the software should be embedded in the drone. For that, we use what we call knowledge distillation to transfer information from one lightweight model to another one, which is more specialized. For that, we propose a feature aggregation method to exploit low-level knowledge acquired by an ensemble of models within a new compact model. The synoptic of the method is given in the next slide. You can see here the synoptic of our strategy. We call it a strategy of grafting and branching together multiple lightweight networks. We have represented the example of two-level hierarchy networks. The first model here is responsible for classifying the different superclass C1, C2, and C3, while the two-level 2 models here and here must classify among the class C1 and among the class C2, respectively. The possibility of termination is represented by the superclass C3. If the network here identifies the image as an instance of the class C3, we consider that it is not necessary to have more precise information, and we can stop the inference directly here. If one of the 2 other superclass of interest is predicted by the first network here, For example, the superclass C1, the branch associated with the superclass of C1 is realized. And we decided the new subclass C11 or C12. It is respectively the same for the class C2 with the subclass C21, C22, and C23. As you can see, the architecture of the branching corresponds to a classical neural network. Here you see the branching minus its initial layers. The initial layers here and here are unused. We call this second level networks cut models. Here is the second level cut models. The cut models are amputated, have been amputated of its initial layers, and it allows us to save valuable time while reducing computation redundancy. It is not. It is to gain times for the inference and the application in field in real time. To realize this structure, we can see that we need to develop some new concept of grafting and branching, and grafting here and branching different network together. This concept will be mainly used in our processing method. As we have seen, the sources are images coming from multispectral cameras with 5, 6, or 8 bands. And this information can be processed separately by channel. We can also work with RGB image transformed in a lab or HSV space. If we decide to process channel by channel, red, blue, reddish by example, the given solution is not optimal because we need as many fully operational neural networks as we have channel, as you can see here. Furthermore, we need another tool to obtain the final decision. It will be more relevant to extract feature in each channel, as you can see here. We can extract the channel in each channel, and to aggregate this feature before using them in a second level neural network. It is the solution that we have adopted. As you can see in the figure, we extract feature at a certain level in the network. We can choose this level empirically, but it is not the optimal solution. We prefer using a well-defined strategy that we will describe later in the slides. The features are then injected into a transformation block to make them compatible with the level 2 network inputs. As you can see, the feature may be different in number. There is N1, N2, and N feature for each network. And they also have a different size, upper L1, lower L1, upper L2, lower L2, etc. So it is important to realize the transformation block to insert the data in the cut model. We must also verify that the output of the transformation block is adapted to the inputs of the cut model, the neural network of level 2, without losing any information before the introduction. To realize this operation, we can choose between two strategies to transform the feature. If the level 1 networks are of the same kind, or if there is no problem of parallax with multiple cameras, we can do four operation. We can realize the resizing here of the feature. We do that with interpolation. Then the concatenation of the layer. We can reduce the size of the feature, the number of the feature by by PCA or autoencoder, but autoencoder slow down the system. So we prefer to use PCA. And then we can introduce the new feature in the level 2 networks. Else, if the networks are heterogeneous, or if there is parallax problems, we will have to prepare the data before concatenation. That means that we need for each channel to do the reduction of the number of features by PCA. Here, as you see, we do also the resizing, and after we do the concatenation of the different layers to be introduced in the networks of level 2. The choice of the grafting and the branching node is important, and information theory can help us to find where we can cut the level 1 network and where we can branch it in the level 2 networks. To find those nodes, we use mutual information, which is a part of the information theory, and especially the MIME method, which is the easiest way to estimate the mutual information. As we can see in the figure here, the neural network is made of different segments, and each segment is made of some layers. Some layers are in the transformation phase. Other layers are in the compression phase, and the last layers are in the analyze phase of the neural network. We have realized the study of the evolution of the mutual information between the different layers of the networks and the inputs. And as you can see in this picture, if we represent the evolution of the mutual information as a function of the layers of the networks, it is possible to identify the different segments and to propose a protocol to graft and branch feature. We propose here to realize the grafting on level 1 network just before the compression segment, and the branching on level 2 at the beginning of the analyze segment. The slide shows the result that we obtain on multispectral images with near infrared and shortwave infrared cameras in the laboratory with controlled conditions and in 1 year, in the same year. The NIRS gives the best result with the band green, red edge, and near, as you can see here in the results. The results are very good because we are in controlled condition and with image collected in the same year. In the lower side of the slide, you can see the result with the shortwave infrared camera. The results are not as good as the NIR because we need new pre-treatment to improve the detection and to use these bands with the NIR bands that we have seen before. But the results are not so bad, between 80% and 93%. As you can see, the results are excellent in the NIR and very good in the sphere when we consider the measurement taken within the same year and in controlled condition. But if we train our models with data from the year N, and we infer on data from year N-1 or year N+1, the performance drops by approximately 30%. So we need further work, and those further works will have two directions. The first direction will be the working on domain adaptation, which means finding the transformation that allows the projection of the data from the year n or the year n+1 into the space of year n-1, if we consider it the reference space, and then we can perform the inference operation. The second direction of research may be the implementation of tools from the information theory to also minimize the mutual information between the feature extracted by different networks, as we can see in the figure below. We can add the extraction, the minimization of the mutual information between the different features extracted in the different networks. The end of my presentation. Thank you for your attention.
Thank you, Eric, for the presentation, and thank you very much for this very clear presentation, even for researchers who less experts in the subject. So it was really understandable. So thank you very much, Eric. Do we have any questions? Françoise, maybe you have a check on the discussion panel, because I can't see it properly. Do not hesitate in putting the presentation.
Yes, there is one common question from Luis. So maybe, yeah.
Yes, you have your question is about acquisition in the field.
Yeah. How are your results on field images?
On field, the results were about between 70 and 80% of detection in the field for the same year. We take the acquisition each time after the harvest, because it is the period where the symptoms are the more visible, and it is the time where we can work in the vineyard, because before there is many people working in the vineyard, and the results are between 70 and 80% for the same year. But if we test our algorithm with data coming from the last year or 2 years before, the result falls also between 20 and 30%, and we go near 50% of detection. Then 50% is not very good, but it is better than human. Human are between 20% and 30%, and we are trying to detect 4 different diseases. We are working on the detection of esquire, of leaf roll, of flavescence dorée. So it is sometimes difficult for us to have better results than 50%. So we are trying to work on a new algorithm that are more robust, and we try to improve the robustness of the algorithm to improve our results. Our goal is to reach 50, 75, 80%, whatever the year, and our partner will be very happy with the result.
Okay, thank you, Eric. We have a hand by Shorpali.
Yes, so, Eric, thank you very much for a very nice presentation. Just to understand how the technique works, I think your detection technique works on the fact that it is mostly the reflectance signal from the exposed leaves. So what if I was thinking of a situation where the infestation of disease and pests is more on the leaves that are below the major part of the canopy and which are not exposed to the sun. So under those circumstances, how do you detect this?
For us, actually, it is impossible. We are working with a company specialized in engineering and in computer science, and they are developing a terrestrial drone, and they are working on the implementation of different camera in the upper side of the vineyard and in the low side of the vineyard. But it is a difficult problem because with the drone, with the aerial drone, we can see only the upper side of the vineyard. As you can see in the presentation, we are trying to find the best angle to see the maximum of the leaves, but it is not always there is not one angles, because the angles are different. It depends on the field, so it is really difficult. And with a terrestrial drone, it is more difficult. There are other problem of the displacement of the robots in the field, but we have not the problem of angles.
Yep. Thank you.
Okay, is there other questions?
Could I just have a question not regarding the method, but so you just mentioned that you are inspecting or analyzing the plants after the grape harvest. So this is quite late. I mean, when in Champagne is earlier than other areas, but how does it affect with the leaf senescence? Or I mean, are the leaves still are not changing the color yet, or how does?
We do this before the degradation of the leaves. We do this just after the harvest, because after the harvest the leaves are beginning to degrade, and so the color change, and we may have confusing symptoms that are only due to the senescence of the leaves. So we do the experiment really just after the harvest. We do also a measurement before the harvest to see if we can see the symptom early in time. But for the moment, it is quasi impossible to see the symptom more than 15, between 1 month before the harvest.
Okay, thank you. Yeah, very interesting.
But there are also many works to do to improve the robustness of the algorithm. So we explore different axes, and the two axes that we are developing in two theses.
Okay. I mean, the conversation can carry on as well in the chat. Thank you, Eric, again.
Thank you.
So now we're going to have another colleague from the same laboratory. It's called Alban GOUPIL. So he's associate professor, so again at the Research Center in Information and Communication Science and Technologies. It's called CReSTIC at the University of France. And you're going to talk about the application of information theory for vegetation cover analysis and decomposition monitoring using hyperspectral imaging. So, Alban, the floor is yours.
Yes, thank you.
Share?
Okay,
Yeah.
My sharing is working, or?
Yeah, yes, perfect.
Yeah, that's okay. Okay, thank you. Well, in fact, when I proposed this title, I didn't realize that it was somehow scary because of the word information theory. And it seems that you will have a lot of equation in the presentation, but I promise that it's equation free. So let's begin with a context. In fact, that's work done during the graduation of Noémie Lafouge. She did her PhD last year. And it's a collaboration between the FAR unit research and the CReSTIC. that will explain the fact that the label of the plots are in French, but it should be understandable. Okay, the objective of this work was to characterize the crop residue on the ground of fields. And first, we aim to find a relationship between the cover rate and the biomass on the ground of the field. That is, we look for a calibration curve which gives the biomass density versus the cover rate of the straw. And next, after that, we hope to follow the dynamic of the decomposition of the residues on the field. To achieve this goal, we got two cameras, veneer cameras, which is a hyperspectral camera, and for the second part, a sphere camera also. And we shot, we took images of wheat and rapeseed straw. And the setup, the acquisition setup is given on the lower part of the slide in field here and in labs here. And our camera is a push-button camera shown in the veneer camera. Okay, the hyperspectral images, in fact, is a three-dimensional image. We have a spatial dimension, with the eye as classical images, but for behind each pixel gives a spectra, which is a reflectance of the light measure. That is for each wavelength. We measure the energy caught by the camera. When we look at the fixed wavelength, we have grayscale images, which gives the energy, spatially distributed energy of the light. So that's the same as color images, but instead of only 3 parameters behind each pixel, we have more than 300 parameters behind. And why are we interested in hyperspectral imaging? It's because we hope that the spectrum provides more information behind each pixel. If we look at the spectrum here of the light on the right, we can see that at specific wavelengths, we have some information on chemical. So, for example, the oxygen, the water, and so on. And our camera, however, stop just behind 1 micrometer, so we only have access to the right part of this figure. Hyperspectral images took a lot of storage space, because you have to store the images, 1 images per wavelength. So it's pretty big, and because of this size and because of the spatial and spectral correlation it gives, we have to design specific process to extract information from this kind of images. Moreover, the images, the camera is also sensitive to the external lighting, so the acquisition is delicate. Okay, so both camera we have is the first, the veneer one, which gives the visible range of light and just behind until the 1 micrometer, and a sphere camera which goes to 2.5 micrometers, more or less. Okay. That's kind of images we have. On the top, we have a classical images, color images taken with a digital camera. And just below, that's a color reconstruction we obtain from hyperspectral imaging. And from these images, we wish to classify each pixel as being a straw or as being a soil. Okay, and from that, we opt to compute the cover ratio of the ground by the residues. And because we will have a calibration curve, we can compute the biomass on the ground also. And next, after that, next, the decomposition level, we opt to deduce the decomposition level of the residue from the shape of the spectrum. So we have some pre-processing to do. We have to extract the spectra of the residue and not of the soil. And we have to build this calibration curve first. So for that, we built a database because, as usual, we need a good labeled database to use algorithm to predict if it's a straw or if a residue or if it is a spectrum. So we develop a methodology given on the left, and in the first part, we try to build a calibration curve thanks to imaging to take image of residue on a blue background. And we will try to extract the spectra of the residue from this kind of picture in an unsupervised way, that is without any manual labeling, because the manual labeling is quite time consuming and error prone. So from this kind of spectra shown here, we have to see which spectra comes from the soil and which spectra come from the residue. And that is where the information theory comes into play. In fact, we adapt an algorithm which is initially tested for galaxy classification. And the idea of this algorithm is to merge pixels into a region. And this merging is done by aggregation, by greedy aggregation. And it stops aggregating region until we have only two kinds of region, in fact. And we hope that these two kinds of region are first the background and secondly the residue. And in fact, more precisely of how this aggregation is done is that the algorithm try to keep as much as relevancy of the image, while it tries to compress it at most. And there is where the information theory is interesting, because it provides tools to quantify relevancy and to quantify the compressibility. I don't know if the word exists, but the fact that we can compress the data. And on the right, you see the result of this kind of the algorithm without any modification. So trying to find galaxy in the image, we have poor results, of course, but with the adaptation we use, we success to separate the image into two parts, the background and the residues. In fact, the red lines here give the border between the region. So in an unsupervised way, our algorithm process pretty well here, and that's fine for us. And to see more precisely how this algorithm works, we can observe the process in what we call information plane. In fact, behind each pixel of this plane, we have a segmentation. So each point is a segmentation, and the algorithm starts with the upper right point, where each pixel is in its own region. And after that, regions are merged together, and the process and the algorithm moves to the left. Here, our algorithm is in blue, and the initial version is in green. What we hope is that we go as most, we get the x-axis as lower as possible, because the x-axis measures the compression rate, okay? And the y-axis gives the relevancy. It's given by the measurement mutual information between the variable. But the y-axis, what we hope is to reach the upper left point, the upper left band, where we have a maximum compression and maximum relevancy. Of course, this point is not accessible, so we try to approach to be as close as possible to this point, until we get only two regions, a background and a residue region. And this part is given by the red cross here. So we see that our algorithm is better than the initial solution, because the final result is higher than the final solution of the previous algorithm. And that's the case for wheat and for rapeseed also. And from this kind of segmentation, we can next look at the mean spectrum of the residue of wheat in this case. And the mean spectrum is given, of residue is given on the top, and of the background is given on the bottom. And we see that both algorithms, the good one is in blue, the first one is in green, and both algorithms give quite the same mean spectra. That means that the algorithm should be pretty sensitive to the difference of spectra to get a completely different segmentation. And that's the same for the background. Okay. And from that, how do we get the calibration curve? It's quite easy. In fact, we fill boxes with blue paper on the background, and we fill that with a straw. We took some images, and we use our algorithm to compute the cover rate. The cover rate is simply the number of pixels classified as residue over the total number of pictures. And we also weight the biomass in the box. We repeat this process several times until the execution of the operator, and we scatter the point, the mass density versus the cover rate on a graph, and we fit an exponential curve given here. And we see that the fit is quite good. That means that we have a calibration curve which is pretty close to the numerical data. And this curve, the exponential curve, is theoretically justified also. Well, but in fact, in field, the background, the soil is very blue. And we have to adapt our solution in this case. So in this case, in fact, we just need to add a small post-processing, a simple linear discriminant analysis, LEA. And with this simple step, we are able to get the correct calibration curve for the data from on the film. And it works even on a classical image color. We also test the solution with another classical unsupervised classification algorithm called the Kamins, which is slightly worse. Okay. So once we got this calibration curve, we would like to know how the decomposition, to know the dynamic of the decomposition of the residue on the field. So how do we try to do that? In fact, we got 4 different decomposition levels, as you see on the right, for wheat on the top, for the rapeseed on bottom. And we try to quantify how, at least to qualify the straw as being in each decomposition level. And in parallel, we also did some analysis in laboratory, advanced analysis, this kind of stuff. And we hope that with hyperspectra, we get this level of decomposition. So unfortunately, with the veneer camera, that's not the case. Here we plot a projection of the spectrum is a 2D, a two-dimensional plane, given by the classical LDA analysis. And each point here is a plot of a residue pixel of the residue spectrum on this 2D plane, and the color gives the decomposition level. And as we see, all the color overlap, and that's a mess. So from that, it's very difficult to classify the spectrum, the spectrum according to the decomposition level. If we look at the mean spectrum, we see that the spectra are pretty close each together. That means that the veneer is not relevant for the decomposition, and it's hard to predict from the spectrum the level of the decomposition. If we try, we have a weak accuracy of only 50% of well-classified spectrum. And this fact is the same for wheat and for rapeseed also. But let's try with a SWIR camera. So we have more information, another range of wavelengths between 1 micrometer to 2.5 micrometer. And thanks to this camera, which is more expensive but much more informative, the class, as we see here, do not overlap except for the last two classes. And because of that, we can predict pretty easily with a simple LDA the decomposition level of the residue. We attain around 3/4 accuracy here. If we plot the mean spectra for each decomposition level, we got this plot, and we see that the spectra are pretty different according to the decomposition level. For example, in the first decomposition level, the first part between 1 micrometer to 1.3 or 4 micrometer is higher than for the other decomposition. And from that, it's possible to predict the decomposition level. So it's more promising method, and it seems to say that we have to look for a SWIR range of wavelengths. If we look how the projection is done, we can look at the loading. So just to see which wavelengths are relevant to the decomposition. So if we take the first axis of the LDA, we see that some wavelengths are weight higher in a positive or negative way. And we see some wavelengths are highlighted. For example, the 1.2 or 1.36 micrometer. And it seems to mean that it measures the quantity of celluloses inside the residue. And we can extract some wavelengths that are meaningful in this case. Also, some wavelengths are, we don't know what it means exactly, but they are also meaningful. That's for the first axis, which permit to separate the first two decomposition level to the last two. And the second axis, which permit to separate the between the first and the second decomposition level, we can also do some analysis of the wavelengths that matters. So hopefully that kind of comforting of this method. Okay, small takeaway of this of our work is that the hyperspectral imaging may be powerful because we have some spectral content which give us the chemical or the biological components, at most we can hope, depending on the range of the wavelengths we look at. And we have some spatial content which give us structural information and which can give us some morphological information of the images of the scene. However, the information, this kind of information is mostly hidden behind the large data cube because there is some noise, of course. The images, the hyperspectral imaging is also very sensitive to external conditions, to the sunlight, etc. The information is also dispersed, diffused into a spatial and spectral correlation. And moreover, we don't have any clear explanatory model of the wavelengths that matters. So that's why the algorithm that works on this kind of data should be adapted or designed for. And we need to take care of the what we call the curse of dimensionality, because each pixel, behind each pixel, there is more than 300 dimensional vector. And in this high-dimensional data space, things are quite strange. For example, if we try to imagine or to illustrate a sphere of 300 dimensional, it looks like more picky, as shown on the right, than a smooth ball as we usually see in our 3D world. And that's where information theory can help, because it provides a relevant tool to work on this dimensionality, and then provides also measurement to quantify the relevancy or the compressibility of data. Okay, so that's a part of figure I plan to use at first before I realized the two mathematical aspects of my presentation. So here are the figure you missed, and here are also a photograph of the father of the information theory, Claude Shannon, which is playing with electromechanical mouse in the maze. So thank you for your attention.
Okay, thank you very much, Alban, and thank you as well for sparing us from very, very technical schemes, and but it was really nice presentation. So I hope there's some questions as well for Alban.
There's nothing in the chat, but
I don't see it in the chat.
maybe I can ask something then, because this is, yeah, okay. I was wondering which language. So, yeah. Because we have been discussing in the previous webinars about hemp and hemp fiber extraction and the rating that is done in the field. And one question was how we could detect the evolution of the rating, meaning the decomposition of the stem tissues. So are you involved in this kind of project as well? I mean, what do you use this decomposition data for?
It was just to follow the dynamics of the decomposition in an easy way, I would say, just taking pictures and try to get the decomposition in the field without doing all the laboratory analysis. And we tried after this kind of analysis to link the spectra with what we get in lab with stuff like Van Sust analysis result. and we try to have the link. But first, we have to be sure that we can do this kind of relation.
Okay, thanks.
To complete as well the question of Françoise, I was wondering, I mean, this is part of a work of Noémie Lafouche, so she finished her PhD, and how are you planning to continue this work? I mean, what are the different actions or what you think is starting first, maybe complete?
For this specific work, in fact, there is no following project, but with the collaboration between FAR unit research and the CReSTIC continue, of course, but on other aspects. And we will use also hyperspectral imaging in some new project with FAR. So we got some kind of expertise of this method that we will apply on other aspects.
Okay, so I'm doing a little bit of publicity. So we have a call inside of the Institute of Exebion, and I think this webinar can be as well a good opportunity to be open to collaboration with Finland within the call. So
yeah, we apply for the call, but for of course emergence, the first one call, and yes, of course, it could be a good idea. Okay.
Okay, so if there's no other questions.
No, there is a
Yes,
Brigitte
yeah.
Chabert has her hand up.
You can take the micro, Brigitte, if you want to ask your question directly.
At least we don't hear you.
Brigitte?
You're still muted.
Can you open the camera maybe to see if there's a problem or we don't hear? Or maybe ask your questions through the conversation. Projects are now running on HAMP with CReSTIC. Okay, Brigitte. Great. Okay. Yeah, we have a lot of work that is done on HAMP, and we do have as well a laboratory that is common between FRD and FAR, so there's a lot of things going on HAMP at the university. So merci, Brigitte. If there's no other questions, maybe we can carry on with the next speaker. Merci, Alban.
Thank you.
So we're moving to Luke presentation.
Yeah.
So Matti will start. So just a few words. So John was presenting it. I mean, in this presentation, he mentioned these research professors in Luke. I saw that you had 47, John, in your slides, and I found in looking at that there are 52 research professors now in Luke. And research professors, they play a key role in promoting Luke's scientific competence and executing Luke strategy. So Matti is one of them, and he's a professor in the future farming technologies, and he has been working on sensors, data analysis, decision-making, and artificial intelligence in precision farming and precision livestock farming. So, Matti, the floor is yours.
Okay, thank you. Thanks a lot. And many thanks for the opportunity to present. So let's see, hopefully the presentation will also run. Okay. It should be okay, I think. So I will be presenting about some of the projects that we are working on related to digital twins for supporting smart farming. I will start with the background. So, I mean, the background really here is that we kind of noticed working in the different projects that with the farmers that you get quite a lot of information from the sensing. So you get quite a lot of information, for instance, about the state of the crops from remote and proximal sensing. but still it is quite challenging actually to make a decision on what to do with that data. So it still remains like very much the decision of the individual farmers. So you get quite a lot of information on the variability of the crop within the field and these kind of things from many software packages, but still, you know, to decide how it affects your fertilizer decisions or irrigation or something, that is actually still quite manual in many cases. So that's why we started a couple of years ago working on this concept of digital twins. So this comes from the industry, and they are digital replicates of the real world systems. And then so it practically means that we are combining measurement data with simulation models or AI models and do decisions in real time. Sometimes the digital twin term is also actually used for offline simulation systems, but we are here talking about real time. And then even though like these farming system models have existed for a long time, that you can actually simulate a farm for scenario type of work and so on. And this is actually quite different, and the models might be similar, but the real time aspect brings quite a lot of differences. And one thing is that, for instance, you are partially operating with future or forecasted data. The other thing is that actually there is kind of a lot of, you could call kind of this data plumbing to put all of the data sources together and then to actually to be usable in the model. So what we are doing now, I will present on the work on that we are combining then this observation and management data with crop simulation models. And I will discuss a little bit our plans on what we do then plan to do with other types of models. So I will present one case study, and then a little bit in the end, a little bit more generally on what we are working on at the moment on this topic. So practically, it is a software development activity as well as a modeling activity. So in order to have something digital, it usually means you need to have software. And so this is actually quite a lot. It's practically you need to develop software to make all of this work. And then in the digital twin, the software is the easy part. And then the hard part, I think, is actually to get the model to work accurately. And then the software I will present today, we combine machinery data, measurement data with the AppSim simulation crop model. So the term digital twin has quite, I think in the past few years, become quite popular also in use in agriculture. And as happens, you get the term and then people start using it. It's kind of nice. So I think it's maybe sometimes useful to think about or at least define on what we are talking about. And there's this quite nice paper on digital twins in smart farming, and this kind of makes the differentiation between different types of systems. So if you are seeing that you have a digital twin that is monitoring the state of the system, these kind of things have of course existed for quite a long time. So in now sometimes some of these, let's say, dashboard type of things have been renamed to, so you have some sensors, you are displaying the status. You could also call this, that would then be called like a monitoring digital twin, that you are not actually supporting any decisions as such. You are mainly displaying the information of the state of the sensors, which can also be useful, but it's not actually what I'm talking about today. And then this prescriptive is a different thing. So here you have a model of the current state of the system, and then you also try to predict the future. And then the key thing here is that you have some intervention decisions. So this is more like, well, it's a decision support system, but I think the digital twins concept from the industry brings us some useful standards and technologies. So you could view this as, in a way, also call it a decision support system, and you have more or less the same thing. And then that's something that we want to work towards, is to go towards this autonomy. Okay, I'm sorry, my neighbor is doing some drilling. I hope it's not too noisy. So then you have this autonomous digital twins. So the idea then is that actually you would be having, for instance, that the model would be controlling a robot. So you would be going towards, let's say, full autonomy, that you have a model that is representing, for instance, a field, and then it is deciding when the robot goes in to sow and to fertilize and harvest and so on. And this is something we've been discussing with Juha, and maybe in the future this will be a reality in farming as well. And you will see in Juha's talk about how the link could be made in robotics maybe. So yeah, I think really the ultimate aim is to go towards the automated decision making. So in order to make good decisions, you actually have to be able to predict what happens, because otherwise you are making a random decision, unless you know, I mean, so the aim is to have a model that can give reasonably good predictions on what's the outcome if you do this level of fertilization versus other level of fertilization or no level of fertilization, for instance. Or if you apply plant protection agent or irrigation. And you have actually quite a lot of, so I tried to make a picture of this, that you have, well, you have many different things. So some of these, like the soil properties, are kind of initial conditions in the model. And then you, of course, you have a weather that changes and actually can change very locally. So even if you have a local weather station, it still doesn't like represent the true weather on the farm, because you could still have like differences between the parcel, and many things that we think that are quite certain are actually still uncertain once you go to this precision farming, to this very like 10 times 10 meter resolution of the field management or something like that. And then also you can somehow observe the plant nutrient content, for instance, with remote sensing or proximal sensing, but still you have some uncertainty. And then you need to be able to forecast then what happens in the future if you don't do it. You want to have a forecast what happens if you don't do anything, and then you want to see if you do interventions, then what is actually the effect, and what's the best time to do these management actions and so on. So that's the aim. And then to have a good prediction, I think you need both good observations and then you need to have good models. And then still, like, of course, in an open field system, the future weather is uncertain, so you still have an aspect that you cannot control. On the same concept could be applied in controlled environment in greenhouses, and then you have less uncertainty about the future state. It then becomes easier to make the prediction. But so far we are mainly working with open field. So here I think the same thing as in the two other talks, that you actually need to have training data. So even if you have a simulation model, it is slightly different from the AI model, in a sense that you have these process-based models that are representing the process, and then but still you need to have training data for calibration and validation. So in a way that you not as much as for a neural network model, because you have a lot less parameter and flexibility, but still you need to have data to make it work. And then I think one thing that I would like to highlight actually, that the observability is very important. So I mean, if you cannot observe the state of the systems, you cannot make good predictions. And then I think very often you see papers and discussions on AI, and then that focuses on algorithms, and that's also very important. But actually then good data, I think in many cases is even way more important than the algorithm. So let's say you cannot fix bad data with a good algorithm. Of course, you can to a certain extent try to do it, but actually there is a limit on what you can do if you are not observing something that is critical, or if your observations are bad. And I think this is in a way that if we think about this going towards this full autonomy, we don't have the full set of sensors, and even for the recommendations for the farmer, we don't have. So we don't have like full set of sensors that would always give us a good idea, or at least the practical farmers don't have. So maybe if we take everything that you can buy, you can get a pretty good set, but it is still not, many farmers would not have it. So I put just an example. So you can observe the leaf area index from the satellite, and then the figure on this box plots are showing how the leaf area index is developing for a field over the growing season. And you can get a pretty good idea, but then actually the picture in the bottom is that what happened, like for this year in one of our test fields, that there was like drought for 4 weeks, so the field was completely dry, and then we had a very heavy rain that it was flooded the next day. And then if you go like for full autonomy, and these things can happen that you are not actually observing. So for instance, I think if you think about controlling something purely based on the satellites, it is actually not feasible, because you don't have a view of the current state. And if you want to go with a robot or something, you need to have a lot of sensors, and then you actually need to have a lot of software to do that. So I think at the moment the feasible thing is that you can make a recommendation for a human based on the satellite data. That will work most of the time, but still the farmer needs to say that, okay, something very drastic happened and you are not doing anything with that recommendation, and then you take the next one. So I will then present this case for one field passes and one test field that we've been doing now with mainly as a software development, but some idea on the calibration. So the start of the modeling process happens that we have a sowing and fertilizing data. So we have the isobus task and made some software for processing that data and then putting these hexagonal zones. We've been using the Sentinel-2 derived leaf area index, which is a published model. And then for the calibration, we have the yield map for the wheat field. So this is wheat, spring wheat production. And then we have a local weather station and a soil map. And from then all of these data sources, the aim was to kind of have software that just going from the data, you have a simulation model. So you have actually the components of the digital twin. And then you have a real-time implementation of the prediction, and then also to see how we can use the calibration. And this is just the first year of data. So then we are doing the calibration and testing on the same data set, something that we are currently working on fixing, but I don't have any results on the newer data. And then we use this H3 grid system. So with the 0.16 hectares, which could be actually quite a feasible management unit in practice also for the fertilizer, because when you are using the centrifugal spreaders, the working width could be something between 20 and 40 and even more. So that actually, like, even you talk about the farmers doing precision farming, but then for the fertilization, even though like model-wise you could go to lower resolutions, then actually the practical application, what the farmer controls is more like 15 to 20 meters, depending a little bit on the system that they have. So we have then developed software, so Python interface from the AppSim simulation model, and then the processing of the isobus task files to get the realized nitrogen rates and the seed rates, and then we have a field boundary. So we first manually create kind of a simulation model that has all of the required components. Then software, we use it to make it this parcel specific. This is like the initialization of the model that could be done on any field, and we are now doing it on larger scale than one field. And then you have weather data, and then you are running the simulation that produces then the nitrogen stress and yield forecast and soil water contents. So like technically the model is producing this, but then the question is, can we make it accurate? And then we have also implemented the way of getting the soil and remote sensing data. And the plan is to use this for data simulations, but we haven't really, apart from experiments, done it so far. And then more practically on the software components, so there's a C# code for reading the isobus task, and then a Python.NET Bridge for interfacing the AppSim simulation model, which I will explain briefly. And then we have a Python library for interfacing the various sensor and remote sensing data sources. And so far we've been using MongoDB database, which we'll replace with a kind of more structured information model in the future. Then we developed this simple user interface. So we decided to use, I think it's quite beneficial, of course. There has been a lot of work on this biophysical crop growth models. So they are representing the plants from different components. So you have for instance, the roots and the stem and the leaves and so on simulated separately, and then you have this nitrogen and water responses. And these work well when you have high accuracy calibration data and not so, like the AppSim is an Australian model, so it doesn't work in Finland without Finnish specific like cultivar parameters and so on. So that is the part that needs to be developed. But anyway, these are big efforts, and then the model have been built and improved over decades and then used very widely. So I think it's very beneficial to have these things and then try to figure out what needs to be adapted for the real-time use. And then why we decided to use AppSim instead of many of the other models. So the reason was mainly that it is very modular. So you can, for instance, replace the soil module with your own model if you want and only use the crop. And then also that it is relatively well documented when it comes to the crop model. So it is possible to interface it for our system. Then for model calibrations, so you need to calibrate the phenological parameters of the crop in a crop model. So we used, in this case, data from one growing season and then the leaf area index and the yield map to see if we can come up with a calibration. And then you see that in some of those hexagonal zones, you are very close after the calibration, and then some zones that are not really captured by the model. And then the other thing is that we are in this, the first calibration, when we calibrate the phenology, we are using the same soil parameters. So actually you in a simulation model, you need to have data, or you should have data of the soil profile of the field up to quite deep, like 1 meter or 60 centimeters or something. But we actually don't have for this field, and then we know there is a lot of variability, and also the farmers would not have this data because it would be quite heavy sampling. So what we did is that first we calibrated with the same soil, and then in the second stage we wanted to see if we can use the information from the soil scan, so the electrical conductivity scan of the soil, then to invert the model. So first we are calibrating the crop, we are happy with the crop, works on average, and then we run the optimizer for the soil water availability, so the lower limit of water content in this case. And then if you do it for the individual hexagons or individual zones, the model clearly overfits. So then we decided actually to use a clustering algorithm to have 8 field zones within the field, and then invert it in that way. And then we know that, okay, based on the electrical conductivity scan, we have some uniform soil area, but we don't know what the actual value is. And this is kind of an approach that has been used in the literature with various data sets on this kind of inversion from not exactly the way that we've been doing it, but as an idea wise. So the idea behind this exercise is to see that, okay, you have data from one growing season, then you try to estimate how the soil would behave and what would be kind of the contribution of the water stress in the growth limiting. And then you try to use those values for the following growing season. So that is something that we will be seeing in the future. It's a little bit unknown whether this is the true value, because there could be other sources as well. But then we see that, okay, if we look at the simulation yield of the initially calibrated just the phenological model, actually we see a decreasing trend between the observed and simulated, and this is why, because the field was not with uniform nitrogen management, it was the farm manager who made the decision, and clearly maybe has allocated more nitrogen to the areas with lower yield potential, and it hasn't paid off in this year. And then when we invert the soil and then run the same process, then we are getting more. So that maybe the takeaway from this is that actually the soil explains a lot of things, so we need to capture both the nutrients and the soil, and the inversion is one way to do it. It's maybe more to say that, okay, what we have done so far, we have built the software pipeline, and it actually works very well for this purpose, and we think like from this first experiments are promising, but obviously you need to do more data, and this is something we are also collecting. So you can look at this paper that basically explains the same thing a little bit in more detail. So I think then we have this Horizon project SCALAC data where we are continuing the work also for yield prediction, and then the data assimilation I think will be a critical part. So we will take data from remote sensing, for instance, the leaf area index and canopy chlorophyll content, and this is developed by the partner Vito in the project, or we deliver it as a service. And then we also have DHI in the project that is delivering this evapotranspiration models, and then we will see how those should be assimilated to the model. So we are collecting some training data. We have Case New Holland yield maps from Belgium, and they are also a partner in the project. And then also some of the data from our research farm, and trying to find a good data assimilation strategy. So data assimilation has been used quite a lot, but often it is used only based on the leaf area index. And we don't think it will lead to good predictions, for instance, on the crop nitrogen content, because it's kind of not, if you just data assimilate that the leaf area from the model matches the leaf area from the satellite, we think you are actually, in the traditional sense, doing the wrong way, and you should somehow try to reverse model the nitrogen availability from the soil and so on, and use that to smartly adjust the parameters of the model. So it's a little bit of a vague explanation, but hopefully in next year or in the future you will see that what the approach is, and also we hope that it will lead to let's say better performance than the current approaches. So yeah, that is, and then also the improving the accuracy of of the simulation. So we've been thinking a lot about the use of multi-source data, just not using on one farm, but also these national variety trials, and then some other remote sensing data sets. And then also we are currently working on, so AppSim is a quite complex simulation model that simulates a lot of processes, and we are now implementing also like a simpler simulation model to compare to see which processes are actually like simulated and calibrated properly, and which could be replaced with a simpler alternative. And then there's a lot of advantages in the simpler modeling that you can, for instance, then combine them with the machine learning approaches with a much higher computational speed, so less complexity, and then you can even do things than combine neural networks with crop models and see how that performs. So all these kind of activities, I think, will be interesting in the future. Okay, so thank you for listening, and happy to take any questions.
Thank you, Matti. Any questions? There's nothing in the chat. Yeah, there is Eric.
Yes, I have one question, and thank you for your presentation. What is the scale at which you wish to work with your digital twin? The larger the scale, the more information you need. And if you want to also follow the soil evolution, you need to implement a sensor at different depths. So it increases the problem. The problem become a problem of power of 3 for the calculation complexity if you increase the size that you want to manage.
Yeah, so we are now, it really depends. So the complexity of AppSim and with the different sensors would be that, if, for instance, if you run a single farm in a 10 times 10 meters, so like the Sentinel-2 resolutions, then maybe you need almost a dedicated computer, not a very heavy one, but let's say a single core per farm. And then if you do with this very light crop model, with less parameters, and we have kind of an efficient implementation, then you could probably run the whole country in one computer. So in a day, because we have a daily time step. So there is a lot of difference in the implementation and the complexity. But actually some of the implementations you can run on a GPU in parallel, and then it actually becomes quite. But yeah, with the AppSim it is more, yeah, with the used resolution, so 10 by 10, it is like, yeah, 100 to 500 hectares probably it is.
Okay.
But because the time step is only 1 day, so even if you do all this assimilation, you need quite a lot of replicates, but still it is, let's say, reasonable to do on farm scale. Yeah.
Thank you.
Any other question? Comment?
Matti, I was just wondering, I have a really non-expert question, but when you're saying that you're working with the Sentinel-2, is that the National Center of Space Studies that you're working with? I mean, how does this work? I mean, is that a collaboration, or is?
No, I mean, the nice thing about the Sentinel-2 is that the data is open, so anyone can just grab the data. Basically, well, if you want to do the whole world, you need a little bit of a computing power. But if you have just some region, there are different services where you can get the data from. And of course, in the SCALAC data project, there is Vito, they are kind of specialized in doing remote sensing, and then they are delivering these services. So it becomes quite easy that you just request the data that you need for specific field parsers. But actually, in our own project, we've been just using the raw. Let's say from the Sentinel Hub service, and you don't need to have any collaboration. It is a hyperspectral image, and if you know how to process that, then you are good to go, I would say. Yeah.
Okay, and another non-expert question as well, and then I leave the other people to ask. But I was wondering, I mean, with the global warming and all the impacts that we see on fields, I mean, how your model can be easily adapted to well, something that is going to be even worse years after years, and how it can be possible?
Yeah, so I think that's a very good question, actually. Of course, our forecast horizon is quite short, and I think in practically these type of models you would, and that's why actually one reason why we want to try to do the calibration using farmers' data. So traditional approach for these models is that the research institutes does a lot of field experiments, and then from that it goes into practice, and that is quite of a slow approach. And then if you can use the data that the farmers have, like a lot of the farmers doing precision farming would have exactly the same stuff that we've been using, then you can basically retrain the model or improve the training with every year. So this year I will retrain the model for the data of next year, and then hopefully it can keep track of the changing. Of course, climate extremes can be a problem. So I think this is like in this decision, of course, the weather is uncertain. I think one thing that will come for specific for Finnish farmers in the future is that we are not really using irrigation at the moment, and probably I think there will be a need to irrigate more, and this is something that you can let's say try to support in the model, or we are kind of trying to at least decouple what is the effect of water and what is the effect of nitrogen, for instance, and then that could be in principle also used to guide irrigation.
Yeah, but that was impressive. I mean, your picture on the flooding on the field, and see that just because of droughts for several months, and then suddenly you have water, and then it's
yeah,
it's
I think like years like last year, that would be very difficult to, in many areas that was quite bad. But I think even, probably because last year we had a very dry spring in a lot of the country, and probably still the irrigation would have helped. Of course, then the flooding comes like next
But
issue.
what is impressive is that that's the kind of pictures that we have in the south of France, but we don't expect that you do have that as well in Finland. So
yeah, sometimes, yeah.
All right,
Yeah.
I don't know if
more and more extreme events, everywhere.
Yeah.
I have also a novice question, because you mentioned that the soil actually is a key factor in modeling all this. How is it? I mean, how does it work? I mean, can you weight the soil? I mean, after different years, you know which plots or which areas are more critical, or how can this be taken? I mean, learning from previous years, many. I don't know if I'm clear.
Yeah. Well, I mean, the approach that we want to use in the future, and I think it might be that you look at basically the satellite data or yield maps from the same field parcel for several years, and then you have the weather data, and then you try to run kind of invert the crop model. So you try to infer what has been the effect of water stress, and then it gives you some information. There are some publications also from France and Australia that this approach has been done, and then of course you have to validate it in a research farm on actual plots. But maybe this can be something. I don't see that the farmers would be in future doing a lot of this deep drilling, because it is kind of expensive. Although there are some services emerging in Europe that do that also for the farmers. But I mean, if the modeling approach kind of works and gives you some, it doesn't even have to give you the true values. It just needs to give kind of the behavior of the soil close enough to be able to work with the specific crop model. Maybe this can be something that then you know at least the areas of the fields and so on. And sometimes the farmers, like, let's say they roughly know it, but still if you roughly know it, it is still not that easy to put it into a software to get these zones. So it is better to get it automatically and then see if it matches on what they are actually seeing in the field. So best option would be sampling, but it is too expensive, at least at the moment.
Okay, thank you.
Thank you very much.
Maybe we move on to Juha's presentation. So Juha is a senior researcher in the group of digital technologies in agriculture in URCA, and his research topics include automation, automation, robotics and AI in different applications in agriculture and forestry. And you also participated in the development of agricultural machines automation standards. So now you will have smart machines. So it's a short title to stimulate our curiosity. So the floor is yours.
Hello, everyone. Can you hear me and see my presentation?
Yes.
Okay. Like already said, I'm a senior scientist and I work in digital technologies in agriculture research group. And I'm a technology researcher and my research topic include machine automation, robotics and IA. So I am an expert on methodology of those topics, not expert in agrology or forestry. And my presentation topic today is about smart machines. Why we do research of intelligent or smart machines? Things are not done badly on purpose, but often a limitation or a problem such as a lack of resources or a complicated process leads to do things badly. And technology in itself doesn't improve the world yet, but how it is used make a difference. And in other words, with the help of technology, the aim is to solve a problem or a limitation that exists in the current ways of working in order to work correctly. Standards are important to make technology to be widely available or commonly used. And the most important standard in agriculture is ISO or ISO 11783. The machine combination has usually components from many different brands. For example, the tractor is manufactured by one brand, the implement is manufactured by another brand, and precision control system is manufactured by the third. And the ISO defines the communication between the different components in tractor implement system. It also defines task control and task file for precision farming. And the task file describes what to do, where to do, how to do, when to do, who does, and things like that. And the task controller is used to control the implement in the field while the human is driving the tractor. Besides of task controller, we think that the same task file can be used also by the robots. And there is no need to make modifications to the original task file. All the necessary information can be included there. What is not normally included in the task files are driving lines because human is driving the tractor, but the standard also includes that information, or it can be included in the task. And the new functionalities, intelligent machines and standards are developed using constructive research methods. And that means that some real-world problem is tried to solve by constructing a new technological solution. And over the past couple of decades, we have made several ISO prototypes together with Aalto University. And in addition to the ISO control system, also intelligent functionalities of the machines has been demonstrated. Nowadays, we have concentrate more on robots. And our biggest robot, Walker, is modified from a standard tractor. Mainly the software is different than in the standard tractor, but many commercial components can be still used. For example, auto guidance and cruise control are the basic functionalities of autonomous driving. And in addition to standard components, it has also sensors for localization and obstacle detections that are installed after. One starting point in our research is that the robot would not be an independent and closed island that can be accessed only through the manufacturer's systems. And that's why we utilize and develop standards such as ISO and EFDI to make robots compatible with the current systems and other robots. In one of our projects, Walker was used for autonomous raking. The idea was that the silage harvesting is a hectic time and skilled labor is hard to find, and that's why the robots are used. And Walker was able to move autonomously along the predefined path, and in addition to that, to control the implement based on location. For example, the work is started and stopped at the correct position. And while working, the Walker is also sending its location and state information to external systems. In this case, the drone was listening and following the tractor. And drone also monitors the surrounding of the tractor. Using machine vision, it classifies the obstacles. And for example, it detects the other tractors. And if obstacle is too close to the robot, it sends the stop command. And in addition to the drone, also the tractor monitors the surrounding using its own sensors. Currently, Walker has 2 3D LiDAR sensors and 1 stereo camera. And the obstacles are detected from the RGB image, and the position of the detected object is measured using combined 3D point cloud. And the RGB image in the left one, and in the right image there is the all 3D points from all 3 sensors, the LiDARs and also the 3D camera, but the ground is removed from the point cloud. And we also have smaller robots. The traditional development of agricultural machinery has led to even bigger machines to save in labor costs. But however, with the autonomous machines, the biggest machine is not always the most efficient solution. And also many labor-intensive work needs small robots to replace the humans. And Turo is fully compatible with the Walker. Same standards are utilized and the same interface can be used also. In our recent project, we demonstrate the multi-robot working, and the Turo was used for fertilization. And you can see in the picture the Cartesian arm that is inside the frame of the robot. In the original project where the Turo was developed, there was a camera and strawberry picking unit installed in the arm. And here is a video that was shown in the camera that was attached in the arm. And machine vision was used to detect the strawberries and also the stem. And the stem is used as a picking point of the strawberry. This image is from laboratory, but the same picking unit was also installed in the robot. The smallest robot that we have is Turo. It's fully electric like Aki, and also the same communication standards are utilized. We developed it in a project where the strawberries are treated using UVC. And UVC is used instead of chemicals, but the treatment has to be done every night. So obviously the autonomous solution is needed because otherwise the labor costs would be too high. It is moving quite slowly through the strawberry tunnels and standing still about 20 seconds when the UVC treatment is done, and then moving 1 meter ahead and then making a treatment to a new area again. So it takes quite a long time to make the treatment to whole tunnels. The localization is based in this robot RTK GPS like all other robots that we have. And because we use the virtual reference station, the correction signal is meant for the agricultural purposes. The namely accuracy is only about 2.5 centimeters. But in practice, the accuracy is within about 10 centimeters in 90% of the time. and clearly that is not enough for this application. And we also assume originally that the GPS doesn't work at all in the tunnels, and that's why we also have 2D LiDAR, which detect the tabletop legs. And extended Kalman filter-based SLAM algorithm was developed for localization and mapping of the tunnels. And another important standard in the agriculture is EFDI. That is a short name for Extended AFMIS Data Interface. And basically, it defines the communication between the tractor and external systems. And this image illustrates the communication what the standard defines. Client can be a tractor or robot or other machines, or it can be a service like FMIS. And the communication is between the clients. So tractor or robot can communicate to other tractor or robot, but originally the standard was developed to communicate between the tractor or task controller inside the tractor and FMIS trailers. The payload is mostly from isobus task, but it is extended so that basically anything can be sent between the clients. In all prototypes, we use EFDI to send the instructions to the robots, and we use also EFDI to remote control the robot using high-level commands. And the instructions are basically isobus task files, as I described earlier, that we use exactly the same that for the robots that is used currently for precision farming. And the high-level commands are start and stop commands at the moment. And the EFDI is a link between the remote operator and the robot. The robot has also user interface that is same inside the robot, in remote office, and also in remote control. We also have a remote control that uses radio frequency for safety purpose, because no one is sitting inside the tractor. So it can be safely stopped using this remote control. And the idea in the standard is that different components are compatible with each other. And when we use this and develop the standards, also our own machines will be compatible with each other. And in a new research project, we can choose a suitable combination of devices and services that are needed on that particular research. We don't need to build everything or a new connection between those. In the most recent project, we utilized the EFDI to connect the robot to external AI service. The sensors that are installed in the robot are utilized more efficiently. And the images that the robot sends are processed in a cloud service that will produce a map where the number of strawberries are shown in each location of the tunnel. And also the ripeness of the strawberries are detected. And the farmer can use that information to predict the yield of the tunnel. And also the researcher can use that information to develop new models of the. As I said earlier, the technology itself does not improve the world yet. And that's why we technology researchers cooperate with researchers from other fields, so that we know what are the things what should be done differently and where the technology should be developed. And as a technology researcher, of course, the more efficient and better use of current devices is also of interest. And for example, artificial intelligence could be used even more for task planning, like Matti already presented to you, and process monitoring and management, so that the devices work more reliable and efficiently on their own. That was a bit shorter presentation than before presentation before me, but thank you for listening. Any questions?
Thanks a lot. This was quite amazing to see for me, non-specialist. Any comment or question? If I may ask as well, what's talking about the how much this kind of robot costs compared to the? I mean, okay, it saves labor work, and but what's about the cost? I mean, like this Turo robot you had. I mean, how much the farmers can afford it, and this kind of robots?
Yeah, we have make a calculations. Are there a cost-efficient machines? Because the Turo was originally developed for strawberry picking, and we calculate how fast it can pick the strawberries and what is the development and cost of building the robot. And one arm that we had in that robot is not enough for to be cost efficient. But if there is 3 hands or arms to pick the strawberries, it is cheaper to use the robot than humans to pick the strawberries. So they might be costly to invest, or the investment can be high, but those can be used many years. So after that, using the robot is cheaper than using humans. Okay. And it's also a matter of because of the corona, it was hard to get enough labor, and that's why there was a situation that we were not able to pick all the strawberries before they were too late. So they were left on the field because there was not enough labor to pick all the strawberries. That's why these kind of systems are also needed.
Okay, Eric has a question or comment.
Yes, I was very interested by your presentation, especially the end of the presentation when we were talking about the application of the robots with the detection of the strawberry maturation. It was one of my works in the past. I was working with a startup to develop some algorithm to detect the maturity of a strawberry. You are working with teams specialized in intelligence artificial, in the development of algorithms that are very specific?
We are using the NatureBots service that we have in Luke, that is developed for a bit different purposes, but they are an expert of computer vision and neural networks that will help us. And also we have an expert of strawberry. So we had experts from different domains or fields combining, working with together.
Okay. Okay, thank you.
I have a question as well. In connection with what as well Eric was just said, I mean, are you already, I don't know, in connection with the possibility to build a startup? Because I mean, I was quite impressed by the type of robots that you have already. So is there possibility to transfer to industry world, or is it too early?
I think that is a bit too early, but it's not impossible. We have a discussion about how to commercialize these developments, but we have not done anything further, just discussions. But it is possible. We have funding instruments that will help how to make this commercial from research. But we haven't yet started that process yet.